Our universe is a strange and wonderful place, filled with mysteries that boggle the mind and challenge our understanding. At the subatomic level, the laws of physics as we know them break down, revealing a world that operates on entirely different principles. A realm of perplexing phenomena emerges, where particles behave in ways that defy our everyday experiences. In the quantum realm, particles can exist in multiple states at once, a concept known as superposition. They can even teleport across seemingly insurmountable barriers, a phenomenon called quantum tunneling. One experiment in particular has captivated physicists and laypeople alike for centuries, the Double-Slit Experiment. It offers a tantalizing glimpse into this bizarre and fascinating world, showing us the dual nature of light. It challenges our very understanding of reality itself, forcing us to rethink what we know. Imagine a world where light behaves like both a wave and a particle, depending on how we observe it. Imagine a world where simply observing an event can alter its outcome, a concept that seems almost magical. This is the world revealed to us by the Double-Slit Experiment, a world that defies conventional logic. It is a world that defies our everyday intuition, leaving us both puzzled and amazed. It forces us to confront the profound mysteries that lie at the heart of the cosmos, mysteries that are as vast as the universe itself. Join me as we delve into this mind-bending experiment, exploring its nuances and implications. We'll explore its implications for our understanding of the universe and our place within it, shedding light on the very fabric of reality. The story of the Double-Slit Experiment begins in the early 19th century, a time of great scientific curiosity and exploration. A polymath named Thomas Young, who was not only a physicist but also a physician and a linguist, set out to unravel the nature of light. At the time, the prevailing scientific consensus held that light was composed of tiny particles, a theory that had dominated scientific thought for centuries. This particle theory was championed by none other than Sir Isaac Newton, whose influence in the scientific community was immense. Young, however, suspected otherwise. He believed that light might instead behave as a wave, similar to ripples spreading across a pond when a stone is thrown into it. To test his hypothesis, Young devised an ingenious experiment that would challenge the established norms of his time. He shone a beam of light through a screen with two narrow slits cut into it, carefully setting up the apparatus to ensure precision. If light were composed of particles, he reasoned, the light passing through the slits should produce two distinct bright bands on a screen placed behind it, much like bullets passing through two holes. However, that is not what Young observed. His results were unexpected and puzzling. Instead, he witnessed a pattern of alternating bright and dark bands, known as an interference pattern, which was completely contrary to the particle theory. This pattern could only be explained if light were behaving as a wave, with the peaks and troughs of the waves interfering with each other, creating areas of constructive and destructive interference. Young's experiment revolutionized our understanding of light, challenging the long-held particle theory and opening new avenues of scientific inquiry. It provided compelling evidence for its wave-like nature, a concept that would later become a cornerstone in the field of optics and wave theory. However, as we shall soon see, the story of the Double-Slit Experiment is far from over. The implications of Young's findings would echo through the halls of science for generations. It would take another century of scientific advancements and breakthroughs, and it would take a revolution in physics, including the advent of quantum mechanics, to reveal the true strangeness and complexity of this deceptively simple experiment, forever altering our understanding of the nature of light and matter. To truly grasp the enigma of the Double-Slit Experiment, let's take a closer look at its setup. Imagine a barrier with two closely spaced slits. A light source is positioned on one side of the barrier, illuminating the slits. On the other side, we have a screen to capture the light that passes through. When light passes through the two slits, it doesn't simply create two bright lines on the screen as one might expect. Instead, it produces a much more intricate pattern. We see alternating bright and dark bands spread across the screen. This is the interference pattern, a hallmark of wave behavior. This pattern arises from the way waves interact with each other. When the peaks of two waves meet, they reinforce each other, creating a brighter band. Conversely, when a peak meets a trough, they cancel each other out, resulting in a dark band. This interplay of constructive and destructive interference is what gives rise to the mesmerizing pattern observed in the double-slit experiment. The double-slit experiment took a dramatic turn in the early 20th century with the advent of quantum physics. This period marked a significant shift in our understanding of the fundamental nature of reality. Scientists discovered that light isn't the only thing that can behave like a wave. This was a groundbreaking realization that opened up new avenues of research and experimentation. Tiny particles such as electrons can also exhibit wave-like properties. This dual behavior of particles was both surprising and revolutionary. This revelation shook the foundations of classical physics and ushered in a new era of scientific understanding. The classical view of particles as tiny, solid objects was no longer sufficient. In a groundbreaking experiment, electrons were fired one by one at a double-slit apparatus. This setup was designed to test the wave-particle duality of electrons. If electrons were truly particles, as classical physics suggested, they should have passed through one slit or the other, creating two distinct bands on the screen behind it. This was the expected outcome based on classical theories. Astonishingly, this was not the case. The results defied conventional wisdom and expectations. Instead, the electrons, just like light waves, produced an interference pattern. This pattern indicated that the electrons were behaving as waves. This suggested that individual electrons were somehow interfering with themselves, as if they were passing through both slits simultaneously. This phenomenon was both perplexing and fascinating. This mind-boggling result demonstrated the wave-particle duality of matter. It showed that particles could not be easily categorized as either waves or particles. It showed that particles, like electrons, could exhibit both wave-like and particle-like behavior. This duality is a cornerstone of quantum mechanics. This concept lies at the heart of quantum mechanics and has profound implications for our understanding of the universe. It challenges our perceptions and continues to inspire new scientific inquiries and technological advancements.